Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Chet. Chet obtained her PhD degree from Hong Kong University of Science and Technology last year. Currently, she is a postdoctoral fellow at the University of Toronto while working as a research associate at the University of Guelph. Today, she will tell us about Bluetooth low energy-based contact tracing as an approach to fight COVID-19 pandemic. Chet, the floor is yours.
Okay. Thank you very much. I would like to share my screen. So, good morning to myself, good afternoon, and good evening to anyone that is from Asia, Moscow, and Europe. Okay. I would like to start by asking a questions. So, when was the last time you keep a listen from your friend, or when was the last time that you stay away from someone else? Is this because you just have a big fight with your friends? Or there are some unpleasant smells that make you keep a distance from others? Well, this might be the reasons in the past when we keep a distance from others, but not this day. This day, we are forced and required to stay and keep a distance, keep a safe distance from others because of the deadly virus. 2020 has been a difficult year for many of us. It changes our lifestyle and distracts us from many activities we like to do previously. I believe many of us would like to go back to a normal life, go back to our workplace and interact with others freely without needing to maintain the social distancing. COVID-19 is a highly contagious virus that spreads very quickly, and one preventive measure, one method that can break the virus transmission chain is through an efficient contact tracing, so that anyone who come into contact with the patient that who has tested positive can quickly self-isolate and quarantine themselves to prevent the virus being further spread to others. So in today's talk, we'll look at how we can fight COVID-19 with Bluetooth low energy-based contact tracing. Here are the outline of today's talks. So the introduction is mostly about contact tracing and why we need contact tracing. Then we will see how Bluetooth low energy comes into the context of contact tracing, and through privacy preserving approaches, centralized and decentralized approach will be presented to explain how the data flowing in and out from your smartphone. Next, we'll look at how we can learn a proximity sensing model with machine learning methods. And we use the data set that we have collected from both smartphone and smartwatch for the experiment. And we'll discuss the experimental result and show you some simple proof of concept prototype as a demonstration before concluding the talk. So basically, why we need contact tracing and why contact tracing is important. Contact tracing, as we all know, is a process to identify the times and places where people have come into contact with someone who has infected with COVID or any epidemic virus. Through contact tracing, these people who are more likely to contract the virus, for example, these people has been tested positive, and anyone who has been in contact for the past few days will be notified about their possible exposures to coronavirus, so that they can take immediate actions to quarantine themselves and get tested. The hope is through this process, we can break the transmission chain of the virus. While contact tracing is important in containing the virus outbreak, current contact tracing is not very efficient And we can see here from the traditional contact tracing rely heavily on human level, and mostly people work in the healthcare industry or those investigators to conduct interview with patients who have been tested positive, and maybe through the phone interview, for example. And the goal is to identify those who have come into close contact with the infected person as soon as possible, so that they can take, so that we can notify them and they can take necessary precaution steps to get themselves isolated and get themselves tested. And this method heavily rely on the information provided by the infected patients to tell who they have come into contact for the past 14 days. Here's the problem. If you are, for example, you are tested positive and you need to recall back who you has been interacting with for the past previous 14 days, can you tell? And considering the short-term memory we all humans have, even for who we have talked to in the previous 3 days, we can't even remember. At least for me, I can't remember who I have talked to in the past 3 days. Maybe if I would like to, I might need to take some time to try to recall it. So rather than relying on our short-term memory, digital contact tracing, on the other hand, use our everyday devices, such as your smartphone, to record daily interactions and store these interactions informations into the digital-based memory, digital-based storage. And these informations can be retrieved automatically once the user is tested positive. And so far, various wireless technologies has been exploited for contact tracing, including GPS, Wi-Fi, and Bluetooth. And among them, Bluetooth is the most popular option and has been widely implemented in many countries. So here are just a small list of countries that has implemented the Bluetooth-based contact tracing. The reason for Bluetooth being so popular is that it is a technology that has been promoted that it's possible to preserve user privacy. And for example, if we compare Bluetooth with GPS technology can reduce the location information. So far, there are only few countries use GPS for contact tracing purposes. So this country, including South Korea, for example, in South Korea, the locations of an infected patient will be shared with everyone in the country. And you might probably to know one that while Wi-Fi sensing could be a possible solution to contact tracing, so far we are not aware of, at least I'm not aware of any country that exploit the Wi-Fi signal for contact tracing. One reason is that not many smartphones support device-to-device communications through Wi-Fi, and chances are some people might in a certain remote location that does not have access to Wi-Fi. For example, the underground metro stations or inside a cave, inside a forest. On the other hand, as we can see here, Bluetooth has been widely adopted by this, just a small list by this country, and this short range of wireless technology is preferred as Bluetooth is almost everywhere and is available in many everyday devices. Just look at the devices you have. They use Bluetooth. Your smartphone use Bluetooth. Your smartwatch use Bluetooth. Your earbud, your earphone, they use Bluetooth. And another thing is that we can see here two of the world's largest technology companies. They are coming together and they are partnered up to promote the Bluetooth-based contact tracing technology. And since these two companies, Google and Apple, are the two big companies that has majority, almost 99% of the user on smartphone market. And that is, if you are not, if your phone is not using Android, then most probably you are using iOS. So there are only less than 1% of users that still using those non-smart handphone. So the partnership between Google and Apple has further pushed the development of Bluetooth-based contact tracing. So while you might be familiar with Bluetooth, we use it to stream. We use a Bluetooth to stream music, to share pictures with one another. But how Bluetooth, in particular, the Bluetooth Low Energy, can be used for contact tracing purposes? That is, how can we use Bluetooth signal to detect the proximity between any two users? Before going further, I would like to give you some idea about Bluetooth Low Energy, and in short, we call it BLE. And BLE is a short-range wireless technology that is readily available in most modern smartphones and smartwatches. There are two communications modes available with BLE, the non-connectable advertising and the connectable advertising. The connectable advertising is what we use every day to discover the neighboring Bluetooth devices, to request for the connections, to perform the handshaking and the device pairing. We have been using this connectable advertising mode to connect with another device, to stream the music, and to share the picture with one another. And the non-connectable advertising is somehow similar to one-way broadcasting, in which any device in the non-connectable advertising mode, it can broadcast the signal, and other device in the broadcasting range can receive the message transmitted by the smartphone, but they cannot establish the connection with the smartphone. In general, when talking about contact tracing, we focus on the first one, that's the non-connectable advertising. And in this mode, every smartphone just keep broadcasting a simple message, for example, saying, "Hey, I'm here," and any nearby devices can hear this message, but they cannot reply to them. More specifically, let's consider the following diagram, in which one smartphone is the broadcaster that keeps announced is present, and another smartphone is a listener. And using the non-connectable advertising mode, the smartphone will broadcast a packet advertising periodically. This packet is known as advertising packet. And the packet is transmitted periodically, governed by this predefined advertising interval set by the designer, application designer. TA. When the another smartphone is in the listening mode, that is when the scanning event is on, it can receive the packet broadcast by the smartphone. And by measuring the signal strength of this received packet, the proximity of the smartphone to the smartphone can be estimated. In particular, the smartphone measures the receive signal strength known as RSS, which can tell the distance relationship between any two smartphones. As shown here, we can see that the RSS decreases when the distance increases. So by manipulating this relationship, we can tell if anyone is within the proximity, anyone is less than 1 meter, or they are actually stay away like more than 10 meters from another person. So rather than using a measuring tab to manually measure the distance of one another, we can use this RSS information to automatically measure the distance and identify and ensure that if any two person is practicing a safe social distancing. And besides proximity, we can also detect the occupancy to check if any user is occupying a certain zone. And this is very important in estimating the number of occupants inside a building. For example, it's not recommended to have too many people crowded inside the same building, and we must have control of how many people should be in a building so that it can help to slow the spreading of the virus spreading. So there are two problems to the BLE-based contact tracing. First, many people are not confident of having a contact tracing app installed in their smartphone. That is, they worry that their life will be under surveillance, and this actually violates the privacy. The second problem is we can see that from the previous diagram about the RSS and distance. The RSS is in fact frustrated a lot, subject to various environmental factors. In this case, how can we have a reliable contact tracing? Before talking about the second problem, let's first examine the current approaches to preserve the user privacy based on the centralized and the decentralized approaches. So we can divide the digital contact tracing into two phases. There's the interacting phase and the tracing phase. So in the interacting phase, the smartphone simply broadcasts a randomized yet unique signature. For example, we have 4 users here, A, B, C, and D, and A is broadcasting a signature packet XA, and B broadcasts the signature packet SB. During this process, the signature broadcast is actually performed in the background, so users do not have to be actively involved during this process. They can just use their smartphone as normal for work, for any entertainment, playing game, chatting with their friend, while having the contact tracing execute in the background. Now that the advertising, this SA, the signature broadcast by its smartphone is unique to each user, and it will be also updated randomly to avoid security attack. The timing diagram here shows the signature generated and transmitted to another smartphone. So smartphone A will generate the signature and then transmitted to smartphone B if, let's say, the smartphone B is in proximity to the smartphone A. And this signature, together with the RSS measurement, will be stored in either the local or cloud storage for at least 14 or 21 days, depending on the rules and regulations set by each country. And for the tracing phase, this tracing phase only happens when someone is diagnosed with COVID. So during this process, the data of the infected person, so for example, user A is infected with COVID, will be used to find a matching signature. So and through this process, like the signature matching process, anyone who has come into contact with user A will be identified and they'll be notified. So here the matching process can be either executed locally on individual smartphone, smartwatch, or on the cloud. So we define the latter approach that use the cloud server to perform the signature matching as the centralized approach. And in centralized approach, each user upload the data and store the data in the cloud cloud. That is, the cloud store the data uploaded by user ABCD, for example, according to the user ID. So when user A is tested positive, it will notify the server, and the server will perform the signature matching computations to identify the list of close contact. Then the server will send the matching result to B, C, and D. So for example, if let's say user B is in close contact with user A, it will receive an alert notification, tell them that they have been exposed to someone who has been tested positive, and the alert notification will give the instruction to user B to isolate themselves and get themselves tested. Whereas for user C and D, they will receive the notification say that they do not expose to any COVID patients previously. To preserve privacy, the data are mostly encrypted before uploading to the central server for storage. On the other hand, the decentralized approach store the daily interaction, this data, the signature observed by smartphone A, B, C, and D on the local storage, either on the local smartphone or the smartwatch. And all this data will remain in the local storage for a certain time period, either 14 or 21 days. And if the data pass this period, it will be considered as expired data and will be erased. It will be deleted from the local storage. Once a user is diagnosed with COVID-19, so again, let's say user A is tested positive, he or she will then upload this data from their local storage to the cloud. And the responsible of the cloud is to distribute this data uploaded by user A to all the other users, B, C, D here. And each user, user B, C, D, they will perform the signature matching computation locally on their smartphone. So if they are matching signature, for example, once the user B receive the data distributed by the cloud, it find that they are matching signature inside its local storage. Then the smartphone will then trigger the notifications locally to alert the user. One thing here is that the data distributed to each user is encrypted, and there is no way for other users to discover the true identity of the infected person. So even though you have the signature uploaded by the user A, you will never know this signature data is actually from user A. Furthermore, if you are identified as a high-risk person as a close contact to the infected person, for example, B here, this information is only available to you locally and not to other users or even to the cloud. As opposed to previous approach that the cloud store the risk of each user. The risk of each user here is stored locally and is only available to each individual. So that's being said, for the previous centralized approach, one can hack into the cloud to check who belongs to the high risk, but it's for the decentralized approach, either you are high risk or low risk is only available to you. And one thing, the exposure notification framework developed by Google and Apple we have seen earlier is also based on this decentralized approach. And to that, many countries, including Canada, UK, etc., they have adopted the Google and Apple framework to provide a decentralized based contact tracing. We can see that people are more willing to install the contact tracing applications when they are confident that the applications is developed with privacy preserving in mind, and with this decentralized approach, and in which they know that all the data were stored in their own local storage and will be deleted after a certain time span. And the next core element to the digital contact tracing is the proximity sensing, which allows us to detect if the user is belong to high risk or low risk. So there are two aspects we'll consider when classifying the exposure risk of a user. So first is the proximity between any two users, and the second is the time they spend together. So intuitively, the risk is high when the person stays very close for a very long time. And the risk is low when the person stays far away from each other for a very short time. Also, the risk is low here. Even though the two persons are very close to each other, maybe less than 1 meter, but the time they spend is very short. That is like, for example, less than 1 second. This is a common scenario that happens almost every day. For example, we might pass by someone on the street, we might pass by a stranger on the street, and maybe the distance we have from the stranger is less than 1 meter, but we won't spend more than 1 second with that stranger. So the risk is actually low, and that's considered another scenario when a person who has worked together, stay in the same building, even though they participate the safe social distancing, they keep a good social distancing from each other, but they spend very long time together. For example, if they spend more than 1 hour together inside the same building, this person is more likely to contract the virus. It has much more higher risk than the person who just passed by the stranger. So while we can estimate the time almost correctly based on the number of received packets, it is relatively challenging to estimate the proximity using the always frustrated RSS measurement. So here's the problem. We can see that from this diagram, the RSS fluctuated a lot, even though the distance remained the same. Furthermore, the variation of RSS is different in different environments. The indoor environment, we can see from E1 and E3 has larger RSS variations compared to the outdoor environments. And the RSS fluctuations in the complex indoor environment, for example, room and corridor, which may have multi-path propagations, body shadowing, for example, is most severe in terms of RSS variation compared to the indoor environment with more open space and open area. So instead of model the problem statistically by assuming a certain probability distribution, we suggest to use a machine learning method which can learn a specific model that target a specific environments. The main challenge to the machine learning method is the availability of data set for different environments is limited and most of the time not available. To train a reliable model, we need a large-scale data that can truly capture the environmental dynamic, else the model can learn nothing from the data. So if let's assume the data is available, then intense training is necessary to obtain and optimize a model. The diagram shows here's the training procedures, and the model is only implemented to the smartwatch or smartphone when the model is thoroughly validated and fine-tuned. And the goal here is that given the input vector X that contains the RSS value for those matching signature. We would like to identify if the user is belong to high risk or low risk. So to facilitate the training process, we have collected two sets of BLE data. And one set is based on the smartphone, and another is based on the smartwatch. So for the smartphone data, we build an Android applications that can generate the signature packet according to the decentralized approach we described previously. And here's our applications that allow us to collect the BLE data from the smartphone. And we have two volunteers to conduct the experiment to help us to collect the data. And these two volunteers are required to perform the above these 6 experiments for distance from 0.2 meter to 5 meter. These 6 experiments actually simulate the different combinations of smartphone positions that we might have put in our daily life. For example, two users might hold the phone on their hand, or one on their hand and another put the phone in his pocket, or one on their hand and another put the phone inside the backpack. Here, H stands for hand, P for pocket, and B for backpack. And another experiment we have is to collect the data from Android smartwatch. We program the smartwatch to broadcast the signature data periodically and log all the received packets. And again, we also have 2 volunteers, and they are required to wear the watch on different hands and stand at varying distance from each other. The packet payload and access information are recorded including the timestamp and the MAC address, and both data we have provided both data property and can be accessed from these 2 links. We compare the experiment result with a few state-of-the-art machine learning classifier. And first of all, I would like to show you the experimental result that compare the error rate when determining the distance between 2 users for these 6 different combinations of smartphone positions. We can observe here that the error rate is actually quite high for the case when one user holding the smartphone on their hand and another user has the smartphone inside the backpack. This is intuitive, as when the smartphone is in the backpack, the signal becomes weak. And due to the dynamic hand movement, the RSS value can change a lot. However, surprisingly, we observe that the error is quite low when both smartphone is inside the backpack or inside the pocket. This can be explained that the smartphone in fact stays steadily inside the backpack even though the signal is weak. And by learning the signal pattern, we can learn a model that can actually determine the distance with a small error. Besides determining the distance, we then train a few classifiers to classify the risk according to the distance estimated by the smartphone. And here are just the 3 confusion matrices showing the result obtained from the path loss model, the decision tree, and the LDA, linear discriminator analysis. Here the x-axis indicates the ground truth, and the y-axis the predictions. The diagonal elements show if the model predict the corresponding low risk and high risk correctly. In general, we can see that the machine learning method, this tool can achieve better performance than the path loss model. we can focus on, maybe I would like to talk a little bit about the false positive and false negative. So false positive is basically like when the user is belong to low risk, but then we tell the user that they are actually high risk. And false negative is like the user is actually belong to high risk and it's very likely the user will contract the virus, but then we tell the user, okay, you are safe, you are belong to low risk. So what I would like to say is actually the impact of wrongly classify the user, the impact of having high false negative is very dangerous compared to having a high false positive, because if you can see that if the false positive is high, the user might need to go through a lot of hazard, have themselves tested, get themselves isolated, and then actually they are safe, they are nothing. But then if the false negative is high, we are actually sending the false signal, false message to the user that they are safe, but and they can go out and enjoy their life, but in fact they are bringing the virus to many other people. Similarly, for the smartwatch data, we train for machine learning classifier for two different cases. Here we have the direct and the crosswise case. The direct here means that two volunteers wear the smartwatch on the opposite hands, and when they stand face to each other, it results in a direct signal transmissions between two watches. The crosswise means that both volunteers wear the smartwatch on the same hand. So when they stand face to each other, it resulting in a crosswise transmissions. And this crosswise transmission generally, we can see here, has a lower accuracy compared to the direct one. This is because sometimes the signal can be blocked by human body if using the crosswise transmissions. So in general, in overall, we can see that the smartwatch data produces higher accuracy than smartphone data because smartwatch has less uncertainty than smartphone. That is, users might have different ways to hold their smartphone, put their smartphone inside a backpack pocket or hold it on their hand. But for smartwatch, you either wear it on your left hand or your right hand. So here are two proof of concept prototype we have built to demonstrate the feasibility of our method for contact tracing. In these applications, here, we just want to show that our applications can monitor the social distancing in real time besides logging the data for later classifications when someone is infected with COVID. So for this video, it just shows that when the social distancing is violated, when two persons is they come very close to each other, and alert and notification will be pop up telling them that they are violated the social distancing. So for the first one, since I was working from home that time, I took the video myself, assuming there's another user at the other end with his or her smartphone. Then I slowly walk towards the smartphone, and you can see that the alert message pop up, say that the social distancing is violated. So for the other demonstrations, for the smartwatch, I'm grateful that I have a friend who volunteered herself to help to take the video. So for this demonstration, we purposely stretch out our hand so that our hand is inside the camera. So what I want to say here is that the watch work normally, even though you put your hand down. So we just stretch out our hand so that the smartwatch is inside the camera, and my friend is actually holding the camera, so she do not have extra hand to show you the notification pop up on the watch. Okay, compared to smartphones, compared to smartphone that has many users, smartwatch has lower user penetrations. Hence, the impact might not be that big compared to smartphone-based contact tracing. However, smartwatch has different set of target user. Most smartwatch-based contact tracing is targeting the workplace use cases in which the user might not able to carry their phone when working. Consider many workplaces have slowly reopened. It's important that employer can provide a smartwatch to their employee during work for contact tracing purposes. So here comes the conclusions. As we have been discussed, contact tracing is important to prevent the outbreak of any contagious virus, not only the coronavirus. So it's important for any epidemic that might be happen in the future. What I would like to say here is we should learn from the mistake and should never let year 2020 happen again, as we all have experienced the miserable life of the city or country lockdown. Digital contact tracing is not aimed to replace the traditional contact tracing performed by the healthcare investigator, but as a supplement to minimize the burden of our personal healthcare. So if the digital contact tracing can help you to identify a list of close contact very quickly, it actually helps the investigator to lessen their burden to identify the risk through the further interview with the COVID patients. Furthermore, we can see that this kind of proximity technology with Bluetooth, it is not only available for contact tracing technology, but it can be used for other interactive application. For example, here we show that the smartphone with the Bluetooth, it can tell that whether the user is in proximity with a certain screen, and the screen will adjust the movie content according to the proximity of the user to the particular screen. So I would like to end my presentation. Thank you. And if you have any questions.
Thank you, Chet, for your interesting presentation. We have a lot of questions in the chat.
Okay, I'm checking the chat right now, and so the first question is about the decentralized approach. Should the signature of the infected user be sent to all users? If so, all users shall check whether they meet this signature. So we can go back and. So here for the decentralized approach, we can see that the signature, yes, okay. So for your questions, so we can see that the signature of the infected persons, infected user is sent to the all user. And once receive the signature, for example, the signature from A, then the user, all the other user will check if they say they have received the similar signature in the past. So I'm not sure.
Maybe I can clarify the so if so, it imposes very strict requirements on the transmission networks. So if we have just one infected users, we should notify all the users which use this application that some user is infected. So we need to transmit at least a message over the network to all the users. And also all the users should check over its database whether they need sometime this signature aid. So actually, in my view, it leads to a significant load on the devices to check every time for every infected or for every new infected user. So any ways to address this problem?
Okay, thank you for your question. So basically for the decentralized approach, all the users, they do not have to query or check the cloud every time. So the cloud will actually automatically send the data to all the other users once the cloud receives the data from the infected user. So there's different from the centralized approach in which each user device have to communicate with the cloud very oftenly to check if there's any update. But for the decentralized approach, the user device does not have to communicate to the cloud anytime until the cloud receive any data, and then the cloud will automatically send the data to the user. I'm not sure if this answer your questions.
So the question was about the users B, C, and D.
Yeah.
So each time a new infected user appears, they should go over the database to check whether they have met this signature. So is that true? So each time a new infected user appears in the network, so we need to go over all database in all devices.
No, the database only contains the data from the infected user. So user B, C, D do not have to go to the database. The communication from the database to the user device is like one-way communication. So only the database communicate to the user device, and user device do not have to communicate to the database.
So I mean, the user B still needs to, it has its own database, which signatures it needs over some period of time. Yes? And when it obtains that some user with signature A has been infected, it should go over its own database and check whether there is some matching that's user B meets user A.
Yes, it will go through its own database, and and this process will be performed in the local will be performed locally on the smartphone, so it will not perform on the server.
Yeah, I see. And the question is there any estimation how frequently this infected user appears, and which is the additional load which is required for each smartphone to process this request to database each time the new infected user appears?
I think this depend on how frequent the user will get infected with the COVID, and this data will also different from country to country. So like, for example, the country have the lowest COVID case, so the frequency for the user device to receive the data from the infected person will be quite low, and is not so frequent for the user device to check whether there's any matching signature. But then for those countries with a high COVID case, then I think the frequency for the user device to perform this signature computation will be quite high.
Okay, thank you very much. So other questions from?
Yeah, okay, thank you for your questions. So let's go to the second question. So the second question is from Maxine. So they plans to include types of environments, people in the infection risk classification, example, bus, outdoor, etc. There were articles showing that it has a great impact on the infection risk. Yeah, so I thank you for the question, and this is actually a good question because this kind of environment is very crowded, and then for the bus, for example, we need to commute to work or travel through the bus, and then the bus is always have a lot of people. One example I have come across is the bus transportations in Hong Kong. Actually, they has implemented a certain tab inside the bus, and the tab will keep on broadcast a message that keep track of people that have been on board on the bus. So if they say the particular bus has a COVID patient infected, all the person who has on board in that bus previously will be notified. So I think they have some work on this issue. And for the outdoor environment, I think this is also a good example, and we will consider. I think it's best to consider all the possible environment, but then the primary focus should be consider those environment that has higher chance for COVID infection. For example, the bus environment that the Maxine has mentioned. So Maxine am I answer your questions?
Yeah, it's pretty clear.
Okay, thank you. So we go to the third questions from Dimitri. So Dimitri asks, the question related to atoms questions, how much additional traffic does the decentralized approach generate in comparison with the centralized one? So I would say that the decentralized approach in general generate lower traffic compared to the centralized approach, because if you look at the centralized approach, you can see that all the users keep on sending the data to the cloud periodically every time they observe a certain signature packet. But then for the decentralized approach, the data is only uploaded to the cloud once there's a user infected, and the cloud will distribute the data to all the other users. But the situations might be different when the number of infected user is high. So then the cloud, the communication and the traffic might be very busy, but still, on the other hand, for the centralized approach, the traffic is still the same. What I can say that for the decentralized approach, the traffic is dependent on the number of infections, but then for the I'm sorry, let me try to put it again. For the decentralized approach, the traffic is dependent on the number of infected users. But for the centralized approach, the traffic is the same regardless of the number of infected users. So I hope this answers your questions, Dimitri.
Yes, thank you.
Thank you, Dimitri. And next question from someone whom I don't know how to pronounce your name. So question on slide 28, does high risk versus low risk depend only on distance between users? So we can go to slide number 28. Yeah, I would like to clarify one thing that for our previous, our first experiment smartphone, we only use the distance as the input feature, but for the smartwatch, we further consider distance and time. So I think besides distance, time is also a critical element, as we have discussed for the several scenarios during the presentations. So
okay.
Yeah.
I just at first I thought that you were considering both distance and time, but it turns that in this particular case on the slide, you consider distance only, correct?
Yeah. For the smartphone case, I consider distance only, and then I think consider time is important. So this, I think the performance will further improve if we include the time considerations.
Yes, I agree with you. Moreover, I thought about I think, can you please turn to the previous slide? I think that you had some formulas there.
This one. Oh, I'm sorry. This one?
Yes. So here R is a risk mapping function. So C is the risk.
C is the fitting coefficients. So it's actually the C times the X.
Okay. So the idea I was thinking about is that the device would get the data, for example, the power and the amount of the power of the signal and the amount of the same of signals from the same device, and turn that into a risk number, which reflects how likely is that for a patient to transfer a disease to another person. So I think that might be interesting for future research connected with machine learning.
Yeah, I agree with you. So for future work, I think it's interesting when we can have a different element in define different element for the feature the input vector. So for the input vector, we don't necessarily consider the RSS information, but also the time and maybe some environmental factor that will affect the risk classification at different environments. So
okay.
Yeah, so maybe we go to the next question. Dimitri again. So according to Dimitri, I understand to detect proximity, we need one Bluetooth device to transmit its packet on the same channel. Then another device is listening. How much time the device need to use the same channel? Does this time affect the accuracy of estimation of time the two users spend in proximity of each other? So so for this question, we can look at this actually for the in the non-connectable mode, the smartphone will transmit the signal at channel 37, channel 38, and 39 at the same time, and then after that it will sleep for a certain time and retransmit again on this 3 channel. On the other hand, the listener will scan this 37 or 38 or 39 periodically. So if they say when the smartphone is scanning channel 37, and then when the advertising packet is actually within this very short period, is actually broadcast over these 3 channels. So either way, so either the phone is scanning on either channel, it will still receive the packet transmitted by the phone, and then the time to transmit the packet is very short, because the advertising packet is designed to have a very short range, and the maximum packet that allocated to this advertising packet is no more than 31 bytes.
Thank you.
Thank you. And let's go to the next question by Kiri. It said, was it studied how the amount of training sample influence the trained model performance, and how balanced are the data set? What are the proportion of the data? So thank you for your questions, and this is mostly depending on the training procedures. And then what we can see is what we do actually is that every time when we train the model, we will validate the model and then retrain the model by fine-tuning the parameters. And for the data, since it's a binary classification problem, so we actually try to collect the data such that the data are balanced. So the number of high risk and the number of low risk for the control is actually even. Okay. If I answer your question, and we can go to the next question by Ruslan. So he asks, he has 2 questions. So for the first question, he asks, any packet with proper payload length and random payload is considered as a signature packet on the receiver side. So as I mentioned earlier, so for the Bluetooth advertising packet, actually Bluetooth will define the advertising packet to follow a certain format. So it only allocate 31 bytes for the advertising packet, and then the first few bytes has been used for the header, and there is only a limited by for us to encapsulate the user data, including the signature data. So what we did actually for the signature generation is that we use certain transformation to transform a random data that user generated, maybe 100 lane data generated from the user device and transform it to a smaller size that can fit into the advertising packet. So for the second question, so is it possible to record some signature on the street and upload them to the server as contaminated signature? So this is a very interesting question. I think for so far we didn't consider this, and I agree that maybe sometime when we go on the street we might encounter with someone, and then and the phone will just record the data and send to the the server. So this data might not be actually useful, and it can provide a wrong incorrect identify the cross contact. So I think this would be one interesting direction for future work by considering to some adaptive method to filter out this kind of signature data. On the other hand, I guess there's another method. If we take the time into consideration, then this shouldn't be the problem. So I think there are two possible methods we can deal with this kind of problem. And if you have any suggestions, maybe you can voice it out. If not, then we can go to the next questions. So he said that the pandemic has been around for over a year now. Is there any data showing that the contact tracing turned out to be useful for preventing the disease disseminations? So I have read a lot of articles from the government said that the contact tracing that help the healthcare personnel to identify the risk of cross contact and minimize the possible risk of further spreading. But the successful of contact tracing is also dependent on the willingness of people to install the app. So far, some people are willing to install the app to protect themselves and the loved one, but they are still huge amount of people that are very concerned about the privacy issue with the contact tracing apps. So I can say that the contact tracing app is useful, but the impact is not huge until many people start to participate in the contact tracing. And the next questions by a professor is, he asks, what portions of population that use smartwatches is enough to have some effect on pandemic? All the mentioned apps were installed of less than 1% of device, and they are already active for a much smaller number of devices. So for smartwatches, maybe I think not many people can have a smartwatches, but the smartwatches is actually targeting a different user target. So as we have discussed just now, so we may consider the workplace, for example. So during the work, a certain work, for example, in the factory, so the worker might not necessarily carry the phone always, but then when we consider the factory environment, there are many workers and people will have frequent interactions. So if we want to reopen our workplace, reopen our economy, I think smartwatch contact tracing is very important to prevent the further spread and monitor the people in the workplace. So
just to clarify why I mentioned, thank you for the answer, first of all.
Yeah.
Just to clarify why I mentioned smartwatches, because as you showed, there are a lot of issues with like smartphones or other devices that can be put in back, and so the signal from them will be quite low. And you showed that an error is rather high. Did I understood you correctly?
Can you repeat a question, or maybe I do not get your question?
Okay, so why I mentioned here smartwatches but not, for example, smartphones, because you mentioned that there are many issues with smartphones when they're put in bag, and the signal from them are very small, very low. But as for smartwatches, they're on the hand, and the signal from them is strong enough, and we can map somehow it to the distance. So that's why smartwatches. And the question now is, so how many of them are really important? But okay, if you consider some say closed community like workers and some factory, yeah, it can be done. But as for the population of the city, so I have some doubts about how it can be implemented and on the scale of a city.
Okay, yeah, I agree with you that for the scale of the city, I think smartphone-based contact tracing have much more higher impact than the smartwatches. So I think two of them should come together to actually help for this to improve the contact tracing performance overall as in the country.
Yeah, thank you.
Okay, thank you. And the next question. So, consider a scenario with two people staying left hand. Person A,
hand, not hand. Sorry.
Oh, hand. Okay. Person A, right hand, left hand. B, right hand. So for situation A, person A is wearing smartwatches on the right hand, and person B is wearing smartwatches on the left hand. The distance between their watch is high. Situation B, situation B, person A is wearing smartwatch on the left hand, and A is wearing smartwatches on the right hand. The distance is small, but because of the attenuation, the signal is low. How to distinguish between them? So thank you for these interesting questions, and this currently we actually train two models for these two situations. So for the first model, we consider the situation A, and the second model we consider the situation B. So the thing is that we can use the signal input to identify to know that which situation, and then selectively choose which model to use to do the prediction. So for example, if we know that the signal is somehow belong to two hands in a different hand positions, then model B will be used to do the predictions.
So do you have such models, or it's like your opinion about how it can be solved, this issue?
I think this is interesting issue, because I guess that the limitation we have currently is that on how to select the model. So the problem is like, how can we better estimate which kind of situation that the two user is wearing their watch, and this is one challenge before we can use the particular model to do the prediction. So I think the underlying problem is that first we can separate the problem into two stages. So for the first stages is to identify whether it's the receive signal is belong to situation A or B, and then based on this information, then we further do the predictions.
Thank you.
Thank you. The next question, do you try to reverse engineering of the application used in different countries? For example, you can compare with approach centralized or decentralized are used in different countries for contact tracing. So thank you for your question. So currently we have tried a few applications that are implemented in Canada only. So that actually the COVID watch application in Canada is developed by another university. So we have actually implemented and their application and do the performance comparisons. But for the application developed in other countries, we haven't consider them yet, and so far we only consider the application that based on decentralized approach, and for the centralized approach we also haven't considered them so far. And let's go to the last questions. So did you study the data, how many people are in average infected by a person and how many people are met by one person per day? How efficient is to limit the freedom to all of them? Okay, thank you for this question. So currently we focus on the how we can leverage the boot flow energy, the radio signal for contact tracing, and we did not focus on study how many people that have been infected. I believe there are a lot of study in this area, and there are a lot of paper published in this area, and we can refer to this paper when we would like to know the graph, the data, the infection flow from one user to another user. So I hope I can answer all your questions, and if you still have any other questions, I think you can always send an email to me. And I thank you for this serious interesting discussion section with all of you, and I really enjoy it.
Thank
you
Yeah.
for your interesting talk and for all the answers. I guess the discussion was very productive. Thank you.
Yeah, thank you, everyone.
That's all for today. So thank you.
We have to thank you. Thank you very much.
Yeah, thank you. Yeah, thank you, everyone, for listening and attending to the presentation. I really appreciate it.